Paul, we're glad that you can get here today.
Hi, everybody. Thank you so much. And thanks for that presentation, Florian. Really interesting. This is what I'm going to talk about is very different. Let me share the presentation if I can. So we call this project Sensing the Dynamic Universe. Can you see it? My slide okay there?
Yes, you're good.
And there's our cool new logo.
Do describe that logo. We have about 20% of the participants here cannot see that logo, so please describe.
It would take a while. It's got a it's got a hand which indicates sensing, and an ear with some sound waves coming at it, and this as wavy lines, and the wavy lines appear to be coming from stars. And there's also an eye there. So just to indicate that there are many, many ways to sense the universe, to sense the stars and the quasars and the galaxies. And so it's a project that I've been working on a lot in the last couple of years, but I started it with Wanda Diaz-Merced, who is a blind astronomer from Puerto Rico. And there's a number of collaborators listed here from South America, from the US, and from Europe. And I won't list them all because I know we're running a little late. If you have ever heard of Wanda Diaz-Merced or checked out her projects, that's great. If not, I encourage you to find her TED Talk from 2016, which is really great. It's called How a Blind Astronomer Found a Way to Hear the Stars. And she was here at the Center for Astrophysics for a while, and we got to talking and came up with the idea for this project. So, you know, historically, astronomy has been strongly oriented, or maybe even totally limited to sighted people, which is true even though much of modern astronomy is outside the visual bandpass, right? We have X-ray astronomy, we have infrared astronomy, we have radio astronomy. None of these wavelengths can be seen by the human eye. And now I'm just showing a graphic I put together called Observatories by Wavelength, and it shows a bunch of your classic telescopes on the surface of the Earth, the kind of telescopes you might go to a mountaintop to use, but it also shows space observatories that are needed in many cases to see wavelengths of light that don't make it to Earth, like the Hubble Space Telescope, which registers UV and optical wavelengths, the Chandra Telescope in the X-rays, the Planck Telescope in the microwave range of electromagnetic radiation, etc. And all of these have to get translated in some way to be understood and digested by astronomers and by the public as well. But the amazing thing that's going on right now that's really new is that the whole sky is being mapped by modern telescopes, whose job it is to do that. They take rapid, very large scale pictures of the sky and make these mosaics, these color pictures of the sky. And they're doing it over and over again to make basically color movies of the sky. And what you really get out of that is variables. You find things in the sky that change. So I am showing one picture of the sky now. It's a color image mosaic made by the Pan-STARRS telescope in Hawaii over several years. It shows about 3/4 of the night sky. Took several years to make. And billions of individual stars and faraway galaxies show up as a faint glow in all directions. But you also see this bright arc of the Milky Way galaxy spanning the middle of the image. And there are dark webs of foreground dust that obscure the brighter background glow of stars. And the idea of showing this is just to show you what a wide area survey of the sky looks like. It makes a big sort of spherical looking picture of the sky, almost like a globe of the night sky. But you can zoom in on any tiny portion of it and see hundreds or thousands of stars, quasars, and galaxies. So these all sky surveys make these color movies of the sky, and they can measure objects that are 10 million times fainter than any human eye could see. And at levels of faintness like that, there's probably about 4 billion objects across the sky that can be detected. Again, lots of stars, distant galaxies, quasars, which are galaxies with black holes in the center, etc. Most of those objects by far shine steadily over the course of a human lifetime, but about 1% of them have detectable variability. They change, they get brighter and they get fainter. That 1% means about 40 million variable celestial objects, or objects that are transient. They get very bright and then they disappear forever, or something like that. And so right now there's this explosive growth in this regime of astronomy they call the time domain. Time domain astronomy is happening in a big way. And we want to bring it to the public in an accessible way. So I won't go into detail here. I just have like a table that lists different of these sort of wide area multi-epoch surveys. And the last one that's listed was already mentioned earlier, and it's the Rubin telescope, or the LSST. It's not fully operating yet, but it will be soon. It will revolutionize astronomy and give us such a flood of variable stars and quasars and transient objects like has never been seen before. And so we want to be able to experience what these are about and understand them. So the goals of our project, SDU project, Sensing the Dynamic Universe, is to outline variability. Again, just objects that get brighter and fainter. How common is it? How is it measured? How do we look at it? We use what's called a light curve, right? Which is just the brightness versus time. And what is a spectrum? Like, if we want to understand what each object is, we usually use a spectrum. So we describe that on the web pages, and we also describe different types of variables and transients. So there's a ridiculous variety of different kinds of variables. There are kinds of objects that vary intrinsically. In other words, they actually do get more luminous or less luminous, like exploding stars or pulsating stars or erupting stars or things like that. Then there's a whole branch of variables that are not intrinsically variable, they're extrinsically variable, which means they appear to vary, but that has to do with their sort of geometric orientation relative to us. For instance, a star might appear to be blinking, but it's actually an eclipsing binary star. It's two stars going around each other, and neither of them is getting brighter or fainter, but it looks like it to us because of the geometric orientation. So we talk about that in the website. So it's educational essentially, and it's designed to be useful for students, let's say high school and up, or for the general public who are interested in astronomy. And the primary way we try to make it accessible is by providing sonified video. We provide video of light curves made directly from real data. And also we make sonified videos of optical spectra of these variable objects. So traditional 2D astronomical imaging is a real challenge to convey to the blind on the web. A lot of impressive projects and progress has been made. Excellent for educational purposes, but it can be tricky because the relationship of the sound to the data can be complex. It can also be really inspiring, but sort of impressionistic. And this is one of the greatest sonifications that I know that Kim Arkan and her group have been working on. And this is sonified sound of the center of the Milky Way, an image made from a combination of visual and X-ray data. And it's beautiful, it's musical, and it gives you some idea of what the image is like, but it's hard to know directly what the data is like. So we're gonna try to work with much simpler data in a way and have a much more direct relationship. So time domain data, in other words, brightness that changes with time, can be visualized, and it can also be sonified to benefit people who are blind or have low vision and help them understand variable objects. So we basically started with Sono Uno code, which was written by Beatriz Garcia and Joana Casado in Argentina. And we upgraded it significantly to our purposes with the help of a student, Joe Palmo, who's been working with me. And all that Python code is on GitHub. And here's just an example. I'm showing a light curve of a periodic variable star. It's a kind of variable called an RR Lyra star. And this is a plot of brightness versus time, basically. So on the vertical y-axis is magnitude, which measures brightness. Brighter things are higher up in the plot. And across the x-axis is day in the units we usually use, modified Julian day. And there's a bunch of dots across the plot, and those dots are simply measurements that were taken at a telescope on different days of this same object. And so I'm going to play the video, and a red bar moves across it, which tells you where you are in the light curve and what day is being played. And pitch corresponds here to brightness. The higher the pitch, the brighter the star. So you just hear these measurements that were made. And then actually you hear a gap here because the star went behind the sun and no data was able to be taken during the daytime of the star. And then the measurements begin again. So that's just what an observed light curve of a periodic variable star might sound like. At the end, there's a bell that tells you that there's no more data. And I'm hoping to advance to the next. So if you take that variable data and you try to find a period, a regular amount of time at which it repeats, you can find the pulsation period of the star. and you can put all the observed data into its proper place in phase. The phase of every observation is now plotted. This is a phased light curve of this Aurora Lyra star. There you just heard the star get much, much brighter, and then it slowly fades. And we'll play another phase of it. We play two phases, so you get to hear the shape of the light curve. So that's the light curve of an Aurora Lyra star, and it's quite different from the shape of the light curve of many other kinds of stars. But then we also play the optical spectrum of the star, which is a way to really identify what kind of star it is. And most of you may know that a spectrum is basically just the light from the star that is spread out with a prism or a grating into its constituent wavelengths in a much more highly resolved way. And so we can play the spectrum, and you will be able to hear, first of all, that the intensity of the light starts out high and slowly gets lower. And this is all explained for every object on the website. We start out in the shorter wavelengths, in other words, the blue part of the spectrum, and move toward the red. So since the pitches are higher at first in the blue end of the spectrum, you know that it's a very blue star. But you'll also be able to hear the absorption lines from different atoms and molecules in the star. You'll hear the dips. So let's give a listen to that. Those dips are from absorption of hydrogen lines in the surface of the star. And as the pitch gets lower, that means the energy intensity or the flux is getting lower as we move to the red. So it's definitely a blue star with some strong absorption lines, some dips. Okay, so these are canned videos that we have for many, many different types of variables on the website. And so you can learn about all different types of variables. Sorry, trying to advance the slide here. There we go. The website is available. It's going to go live quite soon, and we're going to make Spanish and Chinese versions of it. As I said, it describes variability itself. It describes many, many types of variables. We emphasize accessibility, especially for people with low vision. And we are basically done building it. Right now, we're super interested in getting some feedback on the usability, the accessibility, and the content itself. We're interested in any suggestions you might have for ways to publicize the website, to use it in different environments. And we're busy working on tutorials and interactive materials for it. So I'm happy to take any questions or any thoughts you have, and please shoot me an email if you want to be in touch about it for any of the reasons I just mentioned. And my email is pgreen@cfa.harvard.edu. I can put that in the chat. So thank you.
Wow, thank you. That was very interesting, and having watched grow up from 2016, it's very, very gratifying. I'd love to see this continue. So questions? Got some thank yous.
Yeah, there are a few different questions in the chat, but I'm curious to know, how was the range selected in terms of pitch? Because I noticed that it sometimes went above my hearing range a little bit. And I was just curious what research you did to determine the optimal pitch
And
for those.
I'll just chime in if you weren't able to see there. I think there was just a blink out on the audio a couple of times too on that while that was going. So I think it would be good to listen to them on the website when you get a chance, Katie. But Paul, go ahead and comment.
Basically, we just ran it by a few people, including Wanda. We did not do significant research on that. Eventually, what we would like to have is people be able to tune the pitch range themselves. But right now, the main effort was to get out the information in canned videos. And to make it as easy as possible for the largest number of people to access it. We are doing a survey right now that we've put together, which takes people through parts of the website, because the whole thing would be a little bit daunting, and ask for feedback. And that's certainly something we're interested in hearing about, because we can go back and fine tune the pitch if we hear in general that it's ranged a little bit too high for people, for instance.
I was wondering, I had a question. Are you working with any musicians or other artists at all, Paul? Because I know that Kim, I know she had to leave the call, but she's mentioned in the past that the survey that they've done on some of the Chandra sonifications, there's a lot of interest in the aesthetics, and people really enjoy, as you described, like the impressionistic kind of mysterious quality, the magical quality of the sonification. So I was wondering if that would also make it more accessible in a way to general users.
Right. Great question. Well, the main musician that we've worked with is me, but I think it's a good point that it might actually be sort of more pleasant for listening if either the tones had a different timbre to it or tonality to it. But we're shying away from using actual, say, notes from a piano or something like that, because again, we want a really direct relationship between the data and the sound. Whereas if you have to map it to a piano pitch, then you're automatically losing a lot of the direct information, rather than just using a simple multiplicative factor to go from, intensity flux to pitch or something like that.
Okay, sure, thanks.
Florian's got his hand up.
Okay, thanks. Thanks, Paul, for the great presentation. I find really interesting this tension between should we use piano notes? Yes, no. Should we have this really direct relationship between data? Yes, no. But because all of these questions kind of appeal to the question of like how scientific can that possibly be, this type of representation and so on. But I would like to pose the science challenge in this type of representations differently. If I have two of these plots, and I could put them next to each other, I could probably even put two plots into one. Can I look at them? Can I extract some features at this point, just visually speaking, and compare them? And then I think science could be done, right? I recognize one thing in one plot, and I recognize that this is different in another plot, and then I can start asking questions, building hypotheses, and so on and so forth. And so that's how it would visually work, I imagine. Yeah, not knowing anything about astroscience. Yeah.
Right.
But what would we need to do in sound to get there? Like, how would we need to represent such a plot so that we could remember what is salient, compare it to the next presentation, find the salient difference, and be able to ask a question, to be able to make an hypothesis for why there is this difference. So,
Right. Great question, and an interesting philosophical kind of dichotomy there, because I think at this point, with the time and the money that we have to work on this project, it's geared more towards education than towards actually doing science. I think that there's great opportunities to do science with sonified data. And because people can hear a lot of things that may be too subtle in the visual representation. Wanda herself was listening to X-ray light curves and able to pick out features in it that X-ray astronomers had missed, for instance. So there's a lot of opportunity for that. This incarnation of the SDU project isn't geared towards like citizen science or towards doing scientific analysis. But I agree, it's totally possible to do, and there's a lot of thinking that needs to go into how you do it. I think you're right that overlapping light curves or spectra from two different kinds of objects would be one way to really highlight the differences. But you'd have to deal with the potential for confusion when you're hearing the light curves of two different objects at the same time. For instance, they would have to have, the points would have to have a different timbre. So you would know clearly this is one star, or this is the other star or something.
There is a good paper about all the different line graph solutions that have been tried and what works and what doesn't work. I can't remember, maybe Bruce, you do. And one of the conclusion was multi-line graphs do not work in sonification, or at least not until now. We haven't found the solution yet.
Yeah, it's hard.
Yeah, it's very hard.
Okay,
yet.
I'm gonna have Sarah go, and then Fia, you had your hand up before, but we'll go with Sarah first.
Hi, first I just wanted to say I really enjoyed that, so thank you. My comment or question, I suppose, is perhaps now, given what you said about the educational and non-scientific purposes of the sonification is maybe less relevant. I guess I was just wondering, so I personally am legally blind, but I also do astrophysics research, and I guess, when I am interested in in a stellar spectrum, I would be interested in not just that there are absorption lines, but where they are, because that's what gives us information. Yeah. I was wondering if there's any way, like when you publish the sonifications online, is there a way for users to get a sense of the locations of the like at what wavelengths there are absorptions, or
that's a great question, and we had talked about that because it could be one way to do that would be to just sort of have as part of the audio background saying what wavelength you're now hearing, so every once in a while it would be like 5,000, 5,500, 6,000 or something, to tell you what wavelength you're at. Or you could do a similar thing to label the lines in the spectrum. Like when there's an absorption line, you might hear, 65, 63, and that's, a hydrogen bomber line or something like that. So again, I think it's doable, and I think it would be a great upgrade. And, absolutely, if you want to talk about stuff like that some more, please get in touch. That'd be great to talk about.
Yeah, I'd definitely be interested. Thank you.
Okay, I am firstly trying to get the information in the chat. All that great. Thank you, Florian, for those citations and papers suggestions. If I am successful at getting it to copy, so it will be in the notes, and it will be part of the meeting recording folder when you put that out. So if we are at almost exactly on time for the ending, so I don't think we have time for too many more questions or comments, but we had a great presentations today. And remember that if you have requests for other presenters, we'll look at possibly getting in one more world chat in May prior to my summer going crazy. We have some great projects going on here at Glass this summer, and I'm really looking forward to reporting on those because some of them include some sonification work. So nice job today, everyone. Thank you. Okay.
Thanks very much.
Thanks for the invitation again. It was great to meet everyone.
Take care.